All right, good afternoon. Welcome back. First of all, Dr. Murphy from the chemistry department is gracing us with his presence today. He heard you guys were the finest class on campus, and he wanted to come see for himself. I said, yeah, they are. Come on in. Couple quick announcements here. Today, we're going to talk a little bit about 5.7, and that's it for chapters 4 and 5. You guys know that you're going to take a test on Monday. Same as always, what that means, all of your OpenStax Blackboard quizzes, any Desmos that you didn't finish, any assignment that you have a 0 or less than full points or anything like that in, you have to have that all done before you sit down at 1 o'clock on Monday to take your test. Let's talk about the one that you just did. I'm going to pull it up. Okay. It says, which of the following functions could represent the function shown in the graph? So, obviously you could graph all 5 of them, and you could try to match pictures and whatnot. But if you just look at that rational function, this is what we looked at on Wednesday. What are some of the key features? Do you recognize the asymptotes? Vertical asymptotes look like they're happening where? 2 and -3. So that tells me that there's probably an equation that has a denominator that's going to equal 0 at both 2 and -3. So out of all those denominators, the only one I see that's going to equal 0 at 2 and -3 is this guy right here. And then the fact that it does have a horizontal asymptote as well. Where does it level off at? Looks like it's going to get really close to the x-axis but never get there, so it's going to level off at 0. So what does that mean? It means that my denominator is a faster horse than my numerator, right? And that's also true for this one, because this is going to be an x squared in the denominator, and this is x to the nothing. It's just a 5. So that shouldn't have been terribly difficult. This guy, it says, which of the following statements would be true? Horizontal asymptote at y equals 0, or the x-axis. Is that going to be true? I think it is, right? Because again, if you compare horses here, numerators and denominators, who's faster? Obviously the denominator. So as we go up to billions and trillions, that fraction is going to get smaller and smaller and smaller and smaller, and it's going to approach 0. So I'm guessing the other 3 are not going to be true. That one's not true. The function has a horizontal asymptote at... Yeah, it doesn't have a vertical or a horizontal asymptote there. Where would this guy's vertical asymptote be? What would make this guy equal 0? X equals 0, right? And the f of 1 is -1. I think I just made that up because Blackboard requires me to have 4 solutions in the multiple choice. Okay, I want you to pull out that the shoe manufacturing worksheet that I gave you. I'm just going to walk you through the solutions here. I'm not going to give you a grade for this. This was just practice, just to get you an idea of what how the asymptote comes into play. So it says, a company manufactures running shoes with a fixed monthly cost of $300,000, and then it costs $30 to produce each pair of shoes. Okay? So, how much does it cost to produce one pair of shoes? Well, they got to pay the $300,000 right away, and then it's going to be an additional $30, right? What happens if they produce 2 pairs of shoes? It would be $300,000 right away, and then it'd be $30 and $30, so a total of 60 plus the $300,000. So it's mass production, right? Like when Nike makes a pair of shoes, they don't just make one of them, they make like 1 million of them, because then it gets cheaper and cheaper per pair of shoes, right? So this would be the total cost function, the $300,000 plus $30 per pair of shoes. So just like the basketball example we did, what would the average cost of a pair of shoes be? Well, it's your total cost divided by the total number of shoes that you make, right? So if you only make one pair of shoes, then your total cost and your average cost is going to be exactly the same. If you make 2 pair of shoes, you take your total cost divided by 2. If you make 100 pair of shoes, your total cost divided by 100 and so forth. So what are we going to do for the average? We're going to take the total, 30 times how many pairs of shoes we make, plus the 300 grand it cost us to build the building and get set up or whatever, divided by X. Okay? So we have I didn't make it in fraction form there, but if you put it in fraction form, it would look like this. 300,000 plus 30x divided by x, and you should automatically recognize the shape of what this is going to make, not just because we were on section 5.6, which is rational functions, but you recognize that it's a fraction, right? So that fraction is going to result in that rational function which you graphed on the last page. So find and interpret and explain your answers. What is C bar of 1,000? C bar means average cost. So what's going to be the average cost if you make 1,000 pair of shoes? Well, you just plug in X, right? This would be 30 times 1,000 plus the 300,000 divided by 1,000. Plug it in your calculator. It would cost $330 per pair of shoes to make those shoes. What happens if they make 10,000 shoes? Then the average would have been 60. What happens if they make 100,000 shoes? Then the average would be all the way down to 33. Do you see how the average keeps coming down? The more they make, the more the average price is going to drop. What is the horizontal asymptote for the graph, and describe what that represents? So, just look at it. Can you guys identify, even without graphing it, you should be able to identify where the horizontal asymptote, where's it going to level off? 30. Use your Horserace Theorem again, right? Who's faster, the numerator or the denominator? Well, they're the same because they're both x to the first power. And when they're both x to the first power, then we got to default to the coefficient. So 30 divided by 1 is 30. So what does that mean? It costs $30 to make every pair of shoes, but you still have that 300 grand hanging out there, right? And that 300 grand is always going to be part of the total cost. But if you spend 300 grand making a factory and putting together a bunch of equipment and materials and all that, and you make billions and trillions of pairs of shoes, pretty soon that 300 grand isn't very much money anymore. It was when you started. When you made 1 pair of shoes, 2 pair of shoes, it's like, holy cow, we spent 300 grand so we could make 2 pair of shoes. We would never do that. That'd be a bad business model, right? But when you make hundreds of thousands and millions of pairs of shoes, all of a sudden, okay, the 300 grand, that's not too bad, right? So you only have to pay that 300 grand, was it monthly or initial? I can't remember. A fixed, every month you got to pay the 300 grand. But still, if you make millions of pairs of shoes every month, so what should that look like? If you graphed it either on your computer or by hand, what it should look like is it's going to level off. This is the key feature of the graph, the red line. It's going to level off at 30. Is it ever going to get to 30? No. It might get to $30.01, or 1/10 of a penny, or 1/100th of a penny, but that 300 grand will always still be in the numerator. So regardless of how big of a number we divide it by, it doesn't quite get to 0, so therefore it's still going to be at 30. So I'll post this for you guys to review. If you want to talk a little bit more about it with me, you can flag me down, but I want to jump to the activity that we're going to do today. So, here we go. You don't need anything other than probably your GeoGebra to graph and a paper and pencil here. Possibly a calculator. Okay, I got about a 10-second video for you to watch. Here we go. 11-second video. Let's watch it one more time. Nope, you got to listen to it. Okay. So here's my question. Question number 1. What is measurable in that video? What variables might be related? Go ahead. The length that it took to stop? That is probably measurable. Anything else?
The time it took to stop.
Time it took to stop? Anything else? If you were the driver, you'd have what in front of your eyes? The speedometer. So you could measure the speed of the car, right? So how could all of those things be related? You guys might be able to make some sense of this. Somebody, I think Jack said the distance that it took to stop. And we also have the speed. We also have the time. Distance and time can kind of go together. How might that be related? Like, how might the distance that it takes to stop be related to the speed of the car when you hit the brakes? Depends on how fast you're going, right? You guys have all slammed on the brakes on the car before? If you're only going 3 miles per hour, not a huge skid mark, right? If you're going 100 miles an hour and you do it, I hope you haven't had to do that, that might leave a longer skid mark, right? So would you guys agree that the faster a car is going, the longer it's going to take to come to a stop? Are we cool with that? That's common sense, right? Okay, I'm going to show you a photograph here. This is, it might be hard to see, this car hit that van. And this is that car's skid mark.
So he tried to stop all the way back there and he still couldn't.
So did you guys hear Katie? First of all, she said he. Do we know it's a guy driving the car?
Whatever.
We'll go with a guy. It's a guy. Okay. So Katie said, you mean he started skidding all the way back there and he still hit that van? The answer is yes. Okay, so here's my first question. I want you to write this down on a piece of scratch paper. How fast do you think that car was going? How fast do you think he was going when he slammed on the brakes? Take a stab at a guess. How fast do you think he was going? By the way, if you can see this little grid, this distance right here is 20 feet. So if that helps you, 20 feet, 40 feet, 60 feet, 80, if that helps you visualize it a little bit. I want to know, I'm going to give you 15 more seconds. You've got to have a guess written down on your scratch paper. Otherwise, you fail today.
Oh, wow.
You've got to have a number written down on your paper in the next 5 seconds. Miles per hour. We're doing miles per hour. I know some of you want to do kilometers, but that's a tremendous question, but I don't know.
I don't know how.
Okay.
What is it?
Really good question I heard back there. Is there a speed limit? We're going to talk about that in a little bit. Okay? Because based on the guess that you're writing down of how fast this person's going, you might already be thinking, I wonder what the speed limit is on that road. Right? Okay. Somebody throw out their guess. 75. I heard 75. Anybody think he's going faster than 75?
Sure. 110.
What do you have, Ella? What'd you put?
80.
80?
110.
110. Anybody faster than 110?
125.
125. Holy cow. Anybody faster than 125? Okay, so that's our highest guess. Okay, what was our first one? 70? 75. Who's lower than 75?
60.
Say? 60. Lower than 60. 55. Lower than 55. 52. Lower? Anybody? Okay, here's our range. We believe he's going somewhere between 52 and 125 miles per hour. We're going to try to figure out exactly how fast he was going. That's our goal for today. Okay? So, let me show you some more information. Well, first let's take a little vote. I need you to vote A, B, or C. Write it down on your paper. I've given you 3 graphs. One is the speed at which the car is going, and the other one is the length of the skid mark that it leaves when the person hits the brakes. Now, they're all 3 increasing, correct? We already said the faster you're going, the longer the skid mark is going to be. So we all know that. But all 3 of them are reflecting that, correct? I want you to vote for which relationship do you believe is most appropriate here. A, B, or C. I'll give you 20 seconds to think about it. Write it down on your paper. A, B, or C. You got 5 seconds. Okay, let's do this the elementary style of voting. Okay? You're going to have to cover your eyes, and when I ask for a letter, you raise your hand if that's what you voted for. Everybody cover their eyes. Ready? Who voted for A? Hands up. Okay, hands down. Who voted for B? Okay. C. Okay. It's D. Okay. A lot of you think it's B. Couple of you A, couple of you C. We'll come back to that. Okay? No, well, for a few minutes. Okay. Now I'm going to give you some data. This is where you're probably going to want to graph some points. Okay? Here is some data. Here are 3 additional crash scenes. Okay? This guy right here, probably a guy, was driving 45 miles per hour, and his skid mark was 101.8 feet. Okay? This guy was driving 56 miles per hour, and his skid mark is 158.8 feet. And this guy was only going 12 miles per hour, and the skid mark was only 7.3 feet. What I'd like you to do is make a little scatter plot with that data, where, if we go back to that other picture, speed's our x-axis, right? Length of skid mark is our y-axis. See if you can make a Geogebra Scatterplot with that information on it. Oh, darn it. It's not what I wanted. I know. Let me just, I wanted to... Okay. Now you guys can see everything you need there. So what points am I going to plot? I'm going to go 45, 101.8. 56, 158.8. And 12, 7.3. And then I'm going to get myself a viewing window that is appropriate so that I can see all 3 of my dots. Does everybody have the data? Can I cover it up? Okay. So here's what my graph looks like. We're only interested in the first quadrant again, right? Everybody got something similar to me? Should have 3 points, right? Okay. Based on your graph, does anybody want to change their A, B, or C vote? What shape does it look like it's going to make? I can't remember what A was. Let me pull it up again here. What is this? What kind of function does that look like to you? It might look exponential, but it's not. Nobody knows what shape this looks like? Does it help if I draw the other half of it? It's a parabola, quadratic, right? Okay. Obviously, that one is linear. This one is actually looks like the opposite of a quadratic, doesn't it? We'll talk about that in a little bit. So, if we agree that this one kind of looks like A, by the way, the 4 of you that voted here, congratulations, you win pride. Okay. How do we get a graph to go through those 3 dots? We have a little tool called fit poly. Remember his command? Fit poly. A, comma, B, comma, C, comma, what? 2. Second degree polynomial, quadratic. And notice it fits like a glove. Goes through all 3 of those points nicely, right? So, I get the following function up in green. If you did this correctly, you should have the exact same function that I have. How we doing? Anybody stuck? So far, so good? Which one are you looking at? Okay. Here we go. So, if you guys see a trend of what we've been doing here the last several weeks, we get data, just like you did on the used car activity. You get some data. You plot that data on a scatter plot, and it gives you a visualization of kind of the relationship between the 2 variables. We use our computer to give us a model that models the data. And then once we have a model, we can use that model to calculate other data that we don't have. Okay? Namely, the original skid mark that I showed you where all of you took that guess at it. That's what we're going to try to calculate here, right? So, here's what I did. This is the data that we used. I came up with, I didn't know what the answer was because this activity didn't come with an answer key. So what I did is I took a picture of, this is our first guy that you guys guessed is how fast he was going when he hit that van. And I overlaid it onto the graph. And I said on GeoGebra, a grid of 1.36 goes with the 20 feet. And on GeoGebra, it was 16.1. So let me make a little proportion for you. So 1.36 on GeoGebra is the same length as 20 feet in real life. So this is on GeoGebra, this is 20 feet in real life. And then on GeoGebra, the skid mark was 16.1. So the question is, how long is that skid mark in real life? Punch it out, see what you get. Calculator might come in handy here. Because if we can figure out how long the skid mark is, we might have enough information to figure out how fast he was going. Anybody got it for me? 236.76. 0.8. Let's go with 0.8. Okay, so that skid mark that we're interested in is 236.8 feet long. What are we going to do with that information? Plug it into what? Back to our GeoGebra. Now here's my question. Is the 236.8 feet, is that an X value or a Y value? It's a Y value. So how are we going to pull this off? Because I can't just plug it in. So Katie wants to make a little line at Y equals what? 236.8. Now we're curious, where does my parabola cross my straight line? So we're going to intersect, and that point is 68.18, 236.8. How fast was he driving? 68 miles an hour, a little over 68. Okay, who was the closest? Who was the closest to 68.18? 65. Was anybody better than 65? Going once? Going twice? Luke, you win. Nothing. Congratulations. Okay. So, just to kind of go with where we're going here. Let me ask you a question that goes with this here. Here's the little sequel to this activity. Okay. When the highway patrol or the forensics experts are on the scene of a crash, do they show up? I have two questions here. Number one, when they arrive at the crash scene, do they measure how far or how fast the car was driving and then use that speed to try to figure out the skid mark length? Or do they arrive and measure the skid mark length and try to use that length to figure out how fast the car was going? Which one is it? It's obviously number two. How are they going to know how fast the car was going if they weren't even there when it happened, right? So they have to use the skid mark to calculate the speed. Do you guys agree? What is our graph set up to do? Let's pretend we didn't know how to do that little y equals trick. Our graph is not set up for that. What is it? I missed it, sorry.
I didn't.
This graph is set up to do what? F of x is set up to input. What's my input? Input speed and calculate skid mark. But that's really not what we want, right? Even though we have a workaround for it. It's called the GeoGebra computer. But what happens if we wanted to do this the other way around? What happens if we wanted this to be skid mark length and we wanted this one to be speed? Wouldn't that then give us a function where we could just plug it straight in without doing that draw the line trick? So how can we turn this function into the other one with flipping my axes? What are we going to do? We're going to find the inverse of this guy, right? Or first, let's just look at the graph of the inverse. We did this way back in section 3.7. Okay? Do you guys remember kind of the mirror image of how an inverse looks? Go ahead and give yourself a line at y equals x. Type in y equals x. And we know that gives us that line that, well, if I size it up, it does the perfect 45-degree angle, right? Cuts that first quadrant in half. Okay, so if we wanted this guy's inverse function, let's just see what it's going to look like first of all. Go ahead and make a new point. Make a new point and put it on your quadratic curve. Mine is point D. And then make sure it's locked in, so when I drag it, you see how it stays on there? Go ahead and lock in point D or whatever point you're on. What am I interested in doing with that point D? I'm interested in his mirror image across the line y equals x. Because right now it's at 31.24, 48.44. If I mirror image it, each point is going to flip the x and y coordinate, and that's what we're trying to do, right? Flip our x and y from skid mark to speed, from speed to skid mark, and so forth. So if you guys remember how to do this, I'm going to click on this mirror image button. It's the third one from the right. And I'm going to reflect it about a line. So that's the one I want. I'm going to click on my point. I'm going to click on my mirror. And now I have a point called D prime. So now as I drag point D around, D prime mirrors him. You guys got your mirror? And then finally, if you want to make it look pretty, go to your D prime, go to right click on it, go to properties, and put the trace on, and now it'll leave its footprint. And what you should recognize now is that dark blue one that I'm drawing is the exact inverse of the original that we made. I'm going to hide this line so it doesn't clutter up my screen. Looks something like that. Okay, I'm going to walk around, see what you got. Flag me down if you're stuck.
For some reason, this point won't move.
You got to move, because you defined it to be D. It's D's mirror. So go move D, and D prime will move automatically.
Oh, okay.
Move D. There it is.
Okay,
Yep.
okay.
Yeah, move your D point, and D prime is programmed to move with D. Now, some of you have the whole bottom half of the graph going over there as well, right? Some of you dragged point D so far to the left. Oh, shoot. Some of you dragged point D so far to the left that you also got this going on, right? So let me just stop at point D. Can we make a skid mark driving negative miles per hour? No. So anything where my miles per hour is negative is non-existent. So the bottom half of my graph really doesn't matter at all. So if you want, on that original, I can go comma x must be greater than 0. So on my original, I just got rid of the left-hand half because I'm not interested in that left-hand half. So now I'm also not interested in the bottom half of my new graph. I'm only interested in the top half. How we doing? So far, so good?
Yep.
We got curves. Okay.
It's right here.
Do you guys remember? We'll talk a little bit about inverse functions. What we've done here is we had an x squared function, right? We started out with a quadratic, an x squared, and then we found the inverse of x squared. Well, what's the opposite of squaring something? Square rooting something. So my green one, my original one, is an x squared, quadratic. My dark blue one that I traced, that's a square root function, right? So go ahead and try this. See if you can actually get a function to graph over your blue trace. So I'll give you this try. We know it's going to be the square root of x, but you're actually going to need a bit of a multiplier to stretch it a little bit. So give yourself a times the square root of x and make a slider. So I'm going to make a slider called a. I'm going to increment it every 0.01, whatever, doesn't matter. And then I'm going to graph a times sqrt x. That's how you do square root of x, sqrt. And now I'm going to see if I can get that guy to match up with the one that I had there. And I'm going to do it by trying to increase my a value. See if I can get it to kind of match. What I'm trying to do is I'm trying to eyeball an inverse function that's going to match the one that I had. That's pretty close. It's a little off at the bottom, but everybody see what we just did? We're trying to make an inverse function of the quadratic. We know that an inverse function of the quadratic is going to be square root. So the question is, what kind of square root is it going to be? So I put a multiplier in front of that square root. To my knowledge, GeoGebra doesn't have the power to just punch in inverse f of x and spit it out. I haven't figured that one out yet. I really wish it could do that. SQRT. If you guys are doing square root of x, in your input bar you got to type SQRT x, and that'll give you the square root. I typed in a times SQRTx and gave myself that slider at a. So I found out that it's about 4.48 roughly models that one. Give everybody a minute to kind of tinker with their computer a little bit here.
If you just reflect the original over the same line, it comes up with that.
Yep. And what does it spit out though? So you reflected the whole darn function?
Yeah.
Okay. I don't know if I've ever done that before. So it's definitely going to match. Does it give you the equation? So I'm going to mirror reflect about a line. I'm going to mirror this guy over this guy. And it gave me a bunch of stuff. It gave me if 0. Yeah, it graphed it, but it still doesn't give you the full equation, does it? Because it's just giving you the...
It shows you where the line's supposed to be.
Yep, it does. Very nice. So if I shut this one off, it still graphs it. Yeah. I've never done that before. Thank you. I learned something today. Do you guys remember back in section, I think it was 3.7, when we were trying to do inverse functions? Like we had one that was like this, y equals 2x plus 3. And we wanted to say, hey, what's his inverse? And we did the little XY switch, where we just say, well, X's and Y's are just going to switch roles. So I'm going to write X equals 2Y plus 3. And then we had to solve for Y. So if I subtract 3, I'd get X minus 3 equals 2Y. Divide both sides by 2, and I'm done. Y equals X minus 3 over 2. This guy is the inverse of this guy. That was a really fast and easy one. Flop the X and Y, and then just solve for Y. Well, you could do that same thing for this guy. Y equals 0.05 x squared minus 0.14 x blah, blah, blah. And because I'm a math nerd, I did it. So I took this guy. There's our car skid equation, the original, not the inverse. I did an XY switch. And then it's a bunch of ugliness, but you got to use the quadratic formula. And you get all the way down to this big ugly down here. So that's what the inverse ends up being, if we could actually punch that in. If I were to punch that in, I would have this exact same graph that I'm showing right here. This one right here. So the moral of the story is a square root function is an inverse of a square function. And that's really all section 5.7 is having you look at, is if you're given a function, can you find the inverse of a function, which we already did way back in chapter 3. And specifically, they're talking about a square root function. I'm going to just refresh your brain about... remember the toothpick example we did? When we did the toothpick example, you might recall that the formula was 1.5x squared plus 1.5x. I don't expect you to remember that. But anyways, when we did the toothpick example, which variable was which? Whoa. Yeah, it was 250 toothpicks. So is 250 my y or is 250 my x? It was the y value, right? X was the number of rows that the guy made with the toothpicks. Y was the number of toothpicks. So remember how we solved that one? We had to cheat. We had to use our computer. We had to go y equals 250, and then we had to intersect it. And then we found out that he can make 12.42 rows. Remember how we did that one? We could do the same thing. This is the same as the car skid one. This one was number of rows. This was number of toothpicks. Car skid, we got speed of the car, length of the skid mark. But we could switch it. What happens if we switched it so that we could enter 250 as the toothpicks and spit out 12.42 as the output? Same thing. It would be the inverse, right? So you would have to know how to calculate the inverse of that function or graph the inverse of that function. And because I'm a math nerd, I did that too. So here's the toothpicks. 1.5x squared plus 1.5x. Switch the x and the y. And then solve for y. The only way to really do this is to use the quadratic formula, which you guys already know how to do. It's a handy dandy tool. I punch it in the quadratic formula, and sure enough, there's the big ugly that it gives it as a inverse. But the same thing can be done with the toothpick example. Okay, I know that was kind of a lot, and some of you were maybe falling behind a little bit on the graphing. What I want you to take away from that is this idea that a square root function, the one that looks like this, is the inverse of the one that looks like this. One's a quadratic, the other one is the inverse, is the square root. And be able to graph that, type it in, whatever. So, I'll stick around for a few minutes if anybody has any assignments or anything that they want to talk about. No, I just wanted you to actually write something down and then not lie about it later. So congratulations there. Make sure you got all your assignments done on Monday, and we'll see you then.